now it's recording. Okay, would you please write that attended? Just write you are attended, or write your name. Okay, just write now on the chat. So those who are absent, they will be recorded as late. Can you please write on the chat there? Okay, just write attended. Yes, attended. Just write like this. That's it. Okay, quickly before and then I will close these. That's okay. All right. Okay. Okay. Today we will discuss the fundamentals. Now you already had this before. Okay, you already covered this in circuits and machines. So then the phasors, instantaneous power. Instantaneous power means that it depends on time. So it's a function of time. When we say instantaneous power, it's a function of time. We have complex power. Complex power has real part and imaginary parts. The imaginary part we call the reactive power. And then also we have the power factors. You're familiar with these all terminology in power systems. And then we'll discuss the network equations, the balanced three-phase circuits. So you all today's topic is you already covered in circuits and machines. Now, what is this one? Maybe I need to share this. This is a rotating. This is rotating as voltage and current. Okay, so we have voltage and current. So the voltage is the blue, for example. They write it as U, for example, or V, as you can see in here. And the current is the red one. They are rotating. If they are rotating anti-clockwise, it means that this one here, the blue or the voltage, is leading the current. Voltage is leading the current because we go anti-clockwise, rotating anti-clockwise this way. How do we know leading or lagging? You stop here, for example, just watch who is moving or which is moving. Stop here. Then you will see if it's anti-clockwise, this blue color here will touch this first, and then the red will touch it. Okay, we'll touch this line, we'll cross this line. So just stop in any line. So I'm stopping here in this line, and these are rotating anti-clockwise. Therefore, this blue color, which is the voltage, is leading the current. So crosses the line before the current, leading the current. In other words, the current is lagging the voltage. The current is lagging the voltage. Now we draw this sinusoidal wave as this one here. So we will forget about this diagram. We will focus on this one. So that's what you will see in your textbook. In reality, it's like this one. Go up. So this touches the first, and then this is the second. So if I stop in here, this comes in, and then this comes in. Okay. So therefore, we draw it like this. So the voltage is leading the current. Where is the current? The current is here. So you can call it a phasor diagram. Okay. So we write in mathematics, we write it like this. Mathematical formula, we write it V max cosine omega t plus V plus delta plus theta. Theta of the voltage. Okay. Or theta of the current. Or sometimes we write theta and delta, for example. That's okay. Theta and delta. Okay, so that we have the voltage and we have the current. This is in mathematical formula, we write it. But we write it in phasor diagram, we write it like this. So what is theta in here? Therefore, we write, or delta, we write it like this. Okay. We put the delta here. Which is delta here? Is this one here? Is the voltage, for example. Okay, is this? So either delta or theta. Okay, so you're already familiar. Any question here before we go on? You're also familiar with this one. We'll not go into the derivation of this one, but at the end, the VRMS, root mean square, is the maximum of the peak, voltage peak over square root of 2 if you follow this one. And this is what you had in circuits. Okay, so we'll also, the terminology is root mean square. Root mean square is the maximum voltage or maximum current over square root of 2. Okay, if we go with these terminology and with the identity, sine square, etc. Okay, so this is just for your information. What I would want you to focus here on of this one. This is what we will use. This is, you already had this in your courses. All right. Again, phasor was just the same thing here. V maximum over square root of 2. And when we say maximum, it's this one. Sometimes we give you, we talk about this. This is the maximum. This is the peak. Okay, this is the peak. So so this is the peak. So this is the maximum. So if you're given a diagram like this one and you want to calculate the RMS, you will look in here. What's the maximum? You will find the maximum in here over square root of 2. Give you the RMS value, or whatever you write it here. You will see a number. Okay, in problems, for example, you will see a number here. For example, 300. So this is the maximum. Always which comes before the cosine is a maximum value. You will not ask this is RMS or not. Okay, always which comes with the cosine or with the sine is the maximum value. So always the number here is the maximum value. And then you will change it into RMS. Okay, over square root of 2. Okay, so this is the same thing here. U of t is just square root of 2 times the voltage, the magnitude of the voltage. Okay, so to make it the maximum, so it's the opposite. Okay, magnitude. So you know this is the RMS value times square root of 2 give you the maximum. Why? Because we're dealing with the cosine part. Okay, so we just go on and on with the RMS, cosine, etc. So this is just like a review for you because we need these, inshallah, later when you do calculations. The time, we have what's time analysis, and we have the phasor diagram. Time analysis means it's a function of time, and you had this in circuits, in the resistor, the inductor, the capacitor, and the impedance. You just add the real part with the imaginary part. So if you have a capacitor and inductor connected together, you subtract them, and the higher value of the inductor, you will put it here. If the capacitance is higher than the inductance, then this will be negative, and this will be the difference. Okay, so this is always like this. So the X is not here the reactance only. It could be capacitive reactance. It could be capacitive. It's not just an inductor here. This could be capacitive inductance, capacitive reactance. So it's just this plus or minus. So plus or negative. Okay. Positive or negative here. So if it's negative, it means this is a capacitive impedance. Capacitive impedance we have, or inductive impedance. Okay, and this way here, plus and Jx, so it is an inductive impedance. Our resistance, we have then the reactance. Of course, then with the magnitude of the impedance, we also need the magnitude of the impedance, is just the square root of the values here, r squared plus x squared, because this is a triangle. The real part, imaginary part, and you found the hypothesis, the z. Okay. And also here, before we go on, this is the theta is always the imaginary part over the real part. Arctan, tan inverse, the imaginary part over the real part will give you the theta of z, the impedance. This is just RL circuit. You're already familiar with this circuit here. Where the idea here, when you have Henry or millihenry, you need to convert it into ohms. To convert it into ohms, you need to go with the j omega L, or just omega L, 2 pi f. So omega L. Okay, x equals omega. So you convert everything into ohms. Okay, Henry or susceptance, for example, farad. Okay, convert it into ohms. Now we're talking, you see, now we are approaching the power. This is what the course is, power systems. So we want you to be really to understand the power. The power is voltage times current. The voltage could be given as this one here. Again, now you will put the maximum because also it is the instantaneous voltage with instantaneous current. And then you will come up with the instantaneous real power. So this is the equation of the instantaneous real power. It's a function of time. Half V maximum, okay, with this one. It's a instantaneous, we call it instantaneous real power. And then you will come with the average power, and you have the instantaneous power, and then we have what's called the average power. Instantaneous power is a function of time. The average power is not a function of time. Okay, there's no function of time. This is a number now. Cosine the angle of the voltage minus the angle of the current. So what is this? Cosine, the difference between the voltage is the power factor. We call the power factor. V times I. These are magnitudes. Are these maximum or RMS? These are RMS. Okay, these are RMS. So, okay, so because of this, okay, so these are RMS value. The power factor is just the angle between the voltage and current. For example, I can maybe draw some here. For example, if the voltage is here, this is V, and the current is here, this is I. This is the angle we're talking about. Okay, this is the angle. So in between. So therefore, if you're given, for example, the angle of the voltage is 60, it means from here to here, 60. I need to change the color. Okay, it means from here to here, 60 degree. And the angle of the current is 45. It comes from here to here, 45. Therefore, the power factor angle is 15. 15. Okay, this part. Okay, it's 15. 60 minus 45. It's 15. And it's lagging power factor. Why lagging? Because the current is lagging the voltage. So we say it's lagging power factor. The current lags the voltage. When the current lags the voltage, if we have a network, an inductive network, motors, for example, motors, industry. Industry, they have motors, large motors. So they need reactive power. So the power factor will be lagging. When we have a network with a capacitive element, or the capacitive network, capacitive means that the capacitance part is higher than the inductance. Then we have a leading power factor. When do we have a leading power factor? In winter, for example. Winter now in Qatar. In Qatar, you do not use your AC, air condition, for example. The air condition is a motor. And the system is designed for summer, for the heavy load. But in winter, it's lightly load. Therefore, the power factor may become leading. Okay? We don't want the power factor to be leading, and we don't want the power factor to be lagging too much. Okay, so 0.87 will be okay. 0.9 is good. The power factor 9 is good. 0.87 is. If you go below, then you need more power to push, as we will discuss later the power. So just now the concept here: voltage is leading the current, or we just focus on the current. Forget about the voltage. Current is lagging the voltage, therefore we have a lagging power factor. Current is leading the voltage, therefore we have a leading power factor. So you just look at one here, which is this one, the current. This is lagging or leading? It is lagging. Why? Because we go anti-clockwise. Right? We are rotating like this. Rotating like this one. So if I stop in here, for example, if you stop in here, this is a man stopping here. Stop here and watch. What will come first? Will come the voltage and then the current. So the current lags. Okay, the current lags the voltage, so it's a lagging power factor. Therefore, you can determine this is an inductive circuit. Okay. Okay, so that's what we discussed here: inductive, capacitive, lagging, leading. Real power could be, this is work, kilowatt, watt, kilowatt, megawatt. Okay, kilowatt, megawatt, watt, kilowatt, or a megawatt. The reactive power, although it's the same thing, by the way, it's just a sign. Real power is VI cosine theta. Reactive power is also VI, which is voltage times ampere. Okay, volt times ampere times sine theta. Sine theta is just a number, dimensionless. Cosine theta is also a number. So this is the real part and the imaginary part. So this is the real part here. And this is the imaginary part, of course, with the VI. So VI times this number, and VI times this number. So it's the same dimension, but we need to differentiate between real power, the same units, but we need to differentiate. That's why we call this is watt or megawatt, and we call this var or kilovar or megavar, which means kilovolt ampere reactive. So we just want to differentiate the units, but it's the same actually. It's the same voltage times ampere times a number. Same thing here times the number. So just differentiate between these. Complex number, complex power is volt ampere. S volt times ampere. Give you so it's just this is the complex number. V times I. V times I. But this would be square root. Okay. Power factor is cosine theta. So as we mentioned here, if current leads the voltage, then the power factor is leading or lagging or at unity. Unity, it means the power is in phase with the current. This is the terminology you use. Okay. The power or the current is in phase with the voltage. When the current will be in phase with the voltage, when we use resistive circuits, such as what? The kettle, for example, you're heating, you heat with water. The heater, for example, in your house, or the space heater, the heater that uses for the room, for example, to heat the room. It's cold, so you want to heat. What you see, the bars there are resistive, converting electricity into heat. Also, when you boil water, for example, in a kettle, this is resistive. So this is in phase. Power factor is 1, which is good. That's what we want. Power factor is 1. Okay, so we always push the power factor to 1. Okay, we always push the power factor to be close to unity. Okay, so if you're using power factor 1, for example, heaters, Kahrama is happy. But if you're using heavy industry, for example, heavy motors, well, Kahrama will not be happy. So you need to install capacitors. So the factories install capacitors to compensate for the reactive power, as we will discuss the compensation later. Okay, so these just how to calculate the complex power, the power, etc. You had, or you already had this one, but you will be questions in the midterm exam quizzes on these those fundamentals. So please make sure that you read them. Okay, these are the questions here. How to determine S, for example. S is P over the power factor. Okay. Power is power factor times S. S is the apparent power. You see now S is V times I cosine theta, but the power, this is S. So V times I is S. Okay. V maximum or maximum is the RMS value, not maximum. We do not multiply the maximums. We multiply the RMS values. All right. Now, this negative here, as you can see, it's very important that you will, when we grade your work, we look for this. It's not just the number. The number is easy, whether you understand or not. You see, this negative here, because of this leading power factor. A load draws 100 kilowatt with a leading power factor. What does it mean, a leading power factor? It gives reactive power. So this circuit here generates reactive power. That's why you will see it's negative. Okay, because it generates reactive power. Reactive power should be absorbed. So therefore we write negative here. Leading power factor. So the Q is negative. If Q is absorbed, this will be positive. So you can tell here Q should be absorbed, should be. Okay. So the conventional terminology. Okay.
Doctor?
So when we say Q, yes, when we say Q is negative, it means that it generates Q. When Q is positive, it absorbs Q. So absorption of Q, the reactive power is absorbed, the power factor is lagging. So the current is lagging the voltage. When Q is absorbed, this is the load, by the way. When we say a load should be what? Should absorb, just to understand, to not be confused now. And when you see, these are things that you need to focus on. The terminology is very important. Let me draw this. You look in here as an engineer. You look here. This is a load. So a load supposed to absorb or to give power? You tell me. Anyone? The load.
Load should
Supposed to
absorb.
absorb.
Yes, absorb. Load.
Absorb. And
Yes.
the generator should absorb or produce power.
No, produce.
Produce power.
Yes.
Okay. Okay, good. So when you see the terminology here is load, and then this is a leading power factor, means that the current is leading the power, then you will put the negative here. Although it will not come in your calculation, will not come negative. It will just give you a number, because this is, you will say sine, cosine inverse of 0.85, for example. And then you will have it, Q is sine. But you put the negative here. How do you know this is a negative? Here, mine, negative 31. 31 is the power factor of this one because of the leading. So you want this to be negative, because the load is supposed to absorb. Suppose means it's positive. Okay, the load is absorbing power, but now it's absorbing minus Q2. The load is absorbing minus or negative 62 kilowatt. What does it mean? Means the load is producing 62. Again, here there is a load. The load is absorbing negative 62 kilowatt. Absorbing negative 62. It means, in other words, it is producing 62 kilowatt. Okay. Yes, what's your question?
Doctor, will it matter if I keep the angle as positive, but just I add the negative to the final answer and say because it's a leading power factor?
Very excellent. Yes, yes, you can do that. Yes, very good. Yes. So the question here, can I just write sign positive in here and put the negative in here, and then I would say because of the leading power factor? Yes, you can do this. No problem. Okay. But this just to give you that's why we get this negative. Okay. Now the reactive power, you see, we need reactive power for the motors, for the inductive, because the motors are inductive load. The motors, your AC, for example, the air conditions, the heaters are resistive. So what is reactive power? Now, what you pay for electricity is you pay for the real power, not the reactive power. You pay for the real power. So what you pay is, so with the useful real power, this is what you pay for. You pay for this part here. But you need this part here. You need reactive power for what? For the motors. Okay, but you want to get rid of it. So factories, they make their motors not to as much as they can to absorb less reactive power, as much as they can, but they cannot. This is 0%. But as much as you can, you want to reduce this one and have useful power, useful real power. So you make it, the more they make it, you want this to be less. But in fact, in reality, so this is a wasted capacity. Wasted capacity for this is as an example to view what is real power, apparent power. Apparent power is the whole thing here, the wasted one and the real power. So the real power will be converted into heat. The real power will be converted into mechanical energy, but this will not be converted to anything. The reactive power will not be converted. Okay, you just need it, and then once you switch it off, that's it. So it goes back to the transmission line. So you need it just for running the motors. Okay, for the reactive power, but it will not be converted. What is converted to heat? What is converted into mechanical power is the real power. Okay, so this one, the useful power here. Okay, that's why this is, we call it wasted capacity. So as an engineer, you will always think that how can I reduce the reactive power? How can I do this? Is wasted for me. Okay, how can I reduce reactive power? How do I know with the power factor correction? Exactly. How do I reduce? Why? Well, we need to reduce it. Why? Because this is the angle here. For example, what we have the real power here, and if this is small, then this much you need. S. This is S, huh? S. And this is the real power. To produce the same now, you need SS. But if it is large, you need this much. Okay, so you need this much S. So therefore, you need, it's the same, to supply the same real power here, the same. You need to push more power. Why? Because you have this reactive power. To push more power. Okay, to supply the same real power. Same real power, you need more power to supply because of this presence here. So we wish to have it like this one and like this one. Real power with S. We wish to be like this. Unity power factor. Okay, conservation of power. At every node, when we say node, this is in circuits, we call it node. In power system, we call it bus. Same concept. Same concept. Okay, so in power system, we call it bus. In circuits, what you had is node. Okay, sum of real power into node must equal 0. So this is the bus now. Sum of real power. What does it mean? It's like the same thing. Sum of all currents entering the node equals the currents leaving the node. That's Kirchhoff current law. And the same concept here. What power is in must be out. Okay. Power in must be out. Sum of reactive power into the node must equal also 0. What does it mean? It means the reactive power into the bus or the node must leave the node also. Okay. Power in equals power out. That's the idea. Okay, which is power in must equal power out. So this is a direct sequence of Kirchhoff's current law and Kirchhoff voltage. Kirchhoff current law, not Kirchhoff voltage. Kirchhoff current law. What is in must be out. This is just another terminology here. What we need, or another slide, just to focus on the real power, imaginary power, or reactive power. Don't say it imaginary power. We say reactive power because not this is okay. So although it's a complex, you don't call it imaginary power. We call it reactive power. Okay, cosine theta. So we call it apparent power, kilovolt ampere, or S. Okay, it's S here. Okay, called apparent power, reactive power, real power. The more reactive power you need, so this will be more here. S will be more. Okay, and then the power factor, as you are familiar with, the real part over the reactive part, kilovolt ampere. Kilovolt ampere. Real part over reactive power, reactive part give you the power factor. And we want this power factor here to be close to unity as much as we can. Okay. Here in electricity or in Qatar, you will see maybe 0.87 in summer. That will be okay. In winter, you might have it at 0.9, 0.95. Okay, so this is just another way to So please read these here, how to find the impedance, for example. When we say impedance, by the way, this is impedance, we call the impedance triangle. It's the same concept of power. But look in here, the impedance triangle, also the resistance and the reactance. Look in here, this, when you go up, it's plus X. So therefore, this impedance here is inductive impedance. This, when you go impedance down, or the reactance is down, negative means negative, down of what? Negative. Therefore, this is a capacitive network. And we call it Y or call it Z, but Z is we call it Z or we call it Y, doesn't matter. So Z equals 1 over Y. Y equals 1 over Z. Okay, so we call it admittance, or we call it impedance. So the same concept, the same concept. Just 1 over Z equals Y. Okay. All right. Okay. And then we'll just use this. You are already familiar with the circuit in here. If you want to find S in here, first of all, what you will do here, this is ohm and this is ohm. The first thing here is to convert all impedances into ohms in the circuit, and then and you cannot add them directly here. This is an imaginary part here. Okay, a complex number. So this is the imaginary part. You cannot add them straightforward here. It's not 4 plus 3. Okay. So what is so S equals V times I. V given. So I is 20, for example, given as this. Now, when you see this 20 minus 6.9 amps, and the voltage here is what is 30. Okay, so this is 30 and this is 6. So this is 30. And this is minus 6.9. The current. Minus 6.9. Okay. Now the angle between them, you add them, because 30 and then it will be 6.9. So this will be 36.9, this one. Okay, the power factor is lagging. Why will be lagging? Either you look at the circuit here, the network here. This is inductance. It's not capacitance. So therefore, the power factor must be lagging. Okay, so when you say 36.9, the power factor is lagging. Current is lagging the voltage. Current is lagging the voltage. So if I stop in here, the voltage comes first. Okay, always stop on the other side. So we stop in here. For example, you stop in this line here. The voltage touches this line before the current. Okay, this line here. We go anti-clockwise. Therefore, voltage touches first, then the second crosses second. Okay, the current crosses next. Therefore, current is lagging the voltage. Okay, or you look at in here, then you can find this. The current is lagging. Okay, and then you will just calculate the power and the S and the Q. Okay, and Q is 1200 bar, volt ampere reactive. Always the units is important when you write the units. Please Don't miss marks just because these are important. 1200 watt. If you just write 1200 watt, megawatt, kilowatt, kilovar, megavar, watt. So you need to write the units. This is var. It's not kilovar. It's not megavar. It's not kilowatt. Same thing for here, 1600. So please make sure that you write the units. Okay, because these are easy things that you will do. So the purpose of giving you this is whether you understand the units, whether you understand the power factor, where just by looking at the circuit, can you determine whether this is lagging or leading? Okay, things like this. Okay. Okay, so similar for circuits, the same thing here. The power in the resistor with I square R. That's why we say I square R losses. Why? No, I square X is voltage drop, also makes voltage drop. So this is with the inductors consume reactive power. It needs there in the inductance. Okay, I square R will be heat. That's why the wire comes hot. The wire comes hot. Why the wire comes hot? If there is a current flows in the wire, because of I square R. I square R is converted into heat. So the wire becomes hot. Here, what does it cause? This one, I square X. I square X becomes the voltage drops. Okay, the voltage drops as you go along the lines or the cables. Okay, again, just you're already familiar with the circuits here. Solve the basic circuits. The reason I put this one here because I would like you actually to review the circuits. This is for your own now to do. Okay, but we just make it simple like this. Okay. Now we come to the power system. The power system, when we draw a power system, this is a generator convention. You are already familiar with the generator. So you draw a circle like this. You don't need to necessarily to put this inside the rotor here, for example. You don't need to put it here. Okay, but this is a power. This is what we call a power system component, single line diagram. Single line diagram, it means that this represents a three phase. But it's one, but we draw it only one instead of drawing three lines. We call it a single line diagram, but it presents three phase. Okay, so these are generators. This is a transmission line, as you can see, transmission line. And then this is a load. This part here is a load. Okay, where we draw from a bus. And this is a node called a node is the bus. Power in equals power out. It goes to the load. Where does it go to the load? It goes there, it converts into heat, it converts into mechanical energy. Okay, to electricity, to lighting, for example, the lights you have. Okay. So this pumps current all the time. Okay, current all the time, pumps current. Or generates current. We say generates current instead of pump, but it's the same concept. So you generate current all the time. All right, so this is a transmission line. This is and when we write here 16 megawatts, 16 megavar, it means that the load consumes here 16 megawatt and 16 megavar. Consumes. When we say load, it means it consumes, absorbs. Generator is producing 17.6 and 28.8. Now, where does it go? Why it reaches here 16.0? It's generated 17.6. خليكم معنا حلوين بصحصحين. These are single a simple thing here to look at, but the way you explain it is important. So what you see here, you will never put here, this is must not be less than this one. Will never be less than 16. This should be equal to 16 or higher. Okay, this part here will never be less than the load. There is nothing free. How you supply the load 16 megawatt from the generation? The generation cannot be 15. Okay. Sometimes when you give them then, and then I ask maybe give any number in insert any number in the generator, any number. They insert 15. That's 16. 15. That's not right. It means that you do not understand what's going on. Okay. The generation must be higher or equal to the load. So where is this 1.6 megawatt? The difference is the losses of the transmission line. Where is this also 28.8 megabar is also the losses of the transmission line. Okay, it reaches 16 megabar. So 12.8 megabar loss of the transmission line because of the inductance of the transmission line. Okay, in this circuit, I'm talking about this circuit here. And we call it a one line or single line diagram. Remember now, draw a single line diagram. It means that you will draw something like this, just one line. Okay, but this represents a three phase. Okay, reactive compensation. You need to include capacitor on the bus. If you include capacitor 16 megabar, because of this 16 megavar, therefore, what power will come in here will come 0 megavar, come here. But what's the power in here will be 6.84 megavar. So what's the losses? Losses here of the transmission line is 6.4 megavar. That's one thing. Second, the voltage here is higher than this voltage. Okay, it's higher. Now we have only 2 minutes left. The voltage here is higher than this voltage. It means that this bus injects reactive power. So the reactive power goes from generation to the load. Now, the voltage, the higher the voltage magnitude, that means that the reactive power will flow this way. The reactive power, Q. Nothing to do with P. And because we have the load here 16 megawatt, also P is also going this way. If this voltage here is 45, that's 45, this is 44.94, and this is 45.9, for example, or 46, the reactive power will go the other way. The reactive power will go here, like this, Q. And the real power will go the other way. So the reactive power will go one way, the active power will go one way, reactive power will go the other way. That's okay. Okay. So not always they are looking at the same, but always the real power goes from the generation to the load. Always. The real power goes where the current flows. The current flows only in one direction. The current cannot be flow in one direction and another current in the other direction. We still have one. Okay. Always the real power goes with the direction of the current. But you don't know where the direction of the current. Okay. So where the real power goes from generation to the load. It means the current flows from generation to the load. What about reactive power? It depends on the voltage magnitude. So it depends on the voltage magnitude. The voltage magnitude is higher, therefore reactive power will flow from higher to lower magnitude. The angle is higher. If this has higher angle, the real power will flow from higher angle to lower angle. Okay. The real power will flow from the bus or from the node that has higher angle to the lower angle, the real power, flow from higher angle to lower angle. So for example, if this one here is 45 and an angle of 0, this must be 40 kilovolt and an angle of minus something, minus or negative, maybe 6, maybe, but negative, must be negative. Okay, I would like you please to register for the attendance, please. Attendance, I will open the attendance for you and please register the attendance. I'll stop.